I am a coastal physical oceanographer, so working on the coastal systems, including the estuaries, bays, and bayous, and tidal rivers and creeks. I don't like to work on the open ocean, the big ones. I like to get, I feel more comfortable when I'm close to the land.
Why is that?
Just that in the open ocean, you have to be very well organized. If you go out to the middle of the Atlantic or the Gulf of Mexico, for example, you need a big boat, big vessel. Then it's gonna usually takes at least 1 or 2 years of the planning to do that.
Right.
And on top of that, once you go out there, things are not that much under your control.
Yeah.
Whereas that in the coastal water, the planning time is shorter and things can be more under control. And at the same time, the topics and issues that you are studying about, they are more related to the everyday lives. So it might not be purely scientific, but it has more practical implications, which I like.
Because it's connected to society and human beings.
That's why I prefer working on the coastal systems. So as a physical oceanographer, I primarily am interested in how and why the water moves. If you look at the water in the Galveston Bay or in the Galveston Beach, the waters are constantly moving. So the physical oceanography is all about the how and why the water moves the way that we observe it.
Right.
So it sounds pretty dull, the movement of the water. But what it really means is that when the water moves, it's not just the water. It carries all the materials in it with it. And then so that thereby the water movement has a huge impact on the movement of the materials of our concern.
Right.
Now, those materials may include some pollutants, like the mercury, or some sediments. In Galveston Bay, maintaining the Houston Ship Channel is a very important activity. So the sediment transport, which is the movement of the sediment, is important. In terms of the ecology, the larva transport, like the oyster larva transport, is a very important, important field. Then the oyster larvae, for example, in a water like this, relatively warm water, they survive as a larvae for about 10 to 12 days. So once they got spawned in the water column, they do not have a muscle strong enough to swim against the current. So they are at the mercy of the current.
Right.
But what they can do is that they have a ciliate. So by modulating the ciliate, they can adjust their vertical position. So, and then many times, depending upon where you are near the surface or you're near the bottom, the current velocity may be different.
Right.
They are aware of that. So that by adjusting the vertical position, they take advantage of the horizontal current to get near to the area which is suitable for their settlement. So if they cannot be there within 10 or 12 days, then we consider them to be lost.
Right.
So that they will not contribute to those yummy oysters that we are eating.
Right.
So that as the water moves, that affects the transport of oyster larvae. So the movement of the water is the very starting point of the many topics and issues in coastal systems. So I've been doing a observational and numerical modeling study of the water movement. The jargon for water movement is called the physical transport or hydrodynamics, physical processes. And then for any given system, let's say Galveston Bay, once I feel comfortable about the understanding why and how the water moves based upon the observational data and based upon the numerical modeling, then I usually like to move on to the modeling of some non-physical the processes, like oyster larva transport modeling, or sediment transport modeling, or the modeling of eutrophication and hypoxia, sometimes the modeling of E. coli bacteria.
Right.
Yeah. So for those the non-physical topics, I have been working with, collaborating with the people in those disciplines, so that they usually take care of the data collection, and then I ask many questions to them.
Right.
So for example, since we've been talking about the oyster larva transport modeling, then I try to read many papers talking about the oyster physiology, oyster larvae physiology, so that what are when they decide to spawn, and then what are the cues for them to move upward or the downward. So this is called the swimming, and this is called the sinking. So I try to read the papers addressing those processes. Many times my knowledge in biology is not good enough for me to understand it alone. Then I'm very good at asking questions. So I go and then ask questions to my colleagues, and trying to carve out the kind of processes that I can put into my model. Yeah. And then I create the model, I run it, and then see that how the oyster larvae will be transported as a function of different conditions.
Right.
Like that, what if the freshwater discharge increases? What if that the wind from the south, the intensifies kind of thing. Yeah.
And in return, are you introducing variables into those biological models that perhaps haven't been studied in biology before? So it's an exchange.
I hope I've been able to, but what the numerical model can do, especially in terms of biology, is that we trying to include the average behavior of those the living organisms into the model.
Right.
Let me make an example. I don't know how familiar you are in terms of the primary production. Those of phytoplankton fixing inorganic carbon dioxide, generating the organic carbon, which is the foundation of the food pyramid.
Right.
And once you get into the living organisms, they are kind of nasty to study about. There's no really the hard, very firm theories about the living organisms. Talking about the physical world, we have a Newton's law, or we have the Einstein's the law of relativity. That those laws we know are fault proof. They are true no matter what.
Right.
But all of those theories are dealing with something that are not living. When it gets down to some living organisms, then the individual differences. If you go to the ladder, the pyramid upward, then some kind of personality kind of thing. Those make a big variability there. So coming back to the primary production by phytoplankton, it is a function of temperature that we all know. Yeah. So the higher the temperature, the more active they become. Yeah. So that they are producing more organic carbon there. Then if you do the lab experiments or the field culturing to see their primary productivity versus the temperature, then the data are everywhere.
Right.
But if you try to find out the average condition, then you can draw a certain curve passing through the middle of the points, right? When you try to incorporate this process called the primary production into your model, you cannot introduce all those variability in the model.
Right.
You can only try to include those mean behavior into the model. So what the model does is that the trying to reproduce in terms of the biology and chemistry, the model tries to reproduce those typical average behavior there. Then someone might ask, why bother to do the modeling? But what's the strong point of the modeling is that it take into account of all the processes. So, for example, in the water, a single phytoplankton, the plankton is a Greek word meaning that the being drifted by the water. That's what the plankton word means. So they don't have any muscle at all. They are 100% at the mercy of the water movement when in the water. So as the water moves, they keeps moving around, And while keep moving around, they do all kinds of biogeochemical processes. It is not easy at all to see all those processes that affect the phytoplankton simultaneously. Numerical model can do that.
Oh, that's neat.
Yeah, but in so doing, all these are but all these are biological processes. What the model attempts to do is to reproduce the mean behavior, not the variability.
And understand how those interact with one another as well.
Yes, the interaction is a very key word in modeling. So I've been working on as I said, the modeling of eutrophication, hypoxia, sediment transport, oyster larva transport, oil spill, and then the E. coli bacteria, all those things. Yeah. And at one point, I submitted a proposal without success about the modeling of the mercury. Yeah. Yeah. So any topics that I think there might be some research money, then I always work with someone in that field.
Right.
So in case of this failed proposal for mercury, there's a guy that specializes in the mercury behavior, how the mercury will be incorporated into the body tissue.
Right.
And then under what circumstances those will be discharged out of the living organisms. The mercury can exist 4 different forms in the nature. As some form, it is very easily digested. As some form, it is very easily excreted. So that there's a scientist studying about all these, and we trying to combine his work with my modeling work to submit a proposal. So I always try to approach any topics like that.
That's really interesting, and it has really important implications for the health and well-being of coastal communities when you start talking about mercury and ingestion and things like that.
So I always consider myself that I can work with anyone. Yeah.
That's good.
Yeah. Yeah.
That's excellent, and we have to be that way in many regards.
Yeah. So and then I used to work on the east coast of the United States, mostly around the Chesapeake Bay area, in the late 80s and then the early 90s, and then 1 year in the 2000 there. Over there, at that time, the biggest buzzword was water quality.
Right.
Yeah, as part of that anoxia in Chesapeake Bay, that's partly because along the Chesapeake Bay, especially the Potomac River, live so many powerful people. They don't like to see the water just in their backyard to be polluted or to be eutrophied.
Right.
Yeah. So they don't like to see the water color turning green or the red.
Right.
So they invested a lot of money. The legislature created the US EPA Chesapeake Bay program. So water quality is a very big field there. So that's when I mostly studied about eutrophication, the anoxia, the submerged aquatic vegetation, and then I came to the Gulf of Mexico. No one seemed to care about water quality here, but the living resources are a big buzzword. Yeah, the oysters, the shrimps, and then redfish. So that's when after working for about a year or 2 in Mobile Bay there, so I saw that the people did not pay attention to me when I talk about the water quality, but they start to pay attention to me when I started to talk about the oyster larvae and then shrimp larvae.
Sure.
So that's how I got into the larval transport business there.
That's interesting because I think it reflects the values that those communities have. Water quality in the Chesapeake Bay area being, like you said, about more elites perhaps that have more money and can afford to care about these things, where on the Gulf Coast it sounds like it reflects the fishing industry.
And now I do understand that there's some legitimate reasons for the people on the Gulf of Mexico not paying that much attention to the water quality, because we have such a much more frequent storm events passing by. Yeah. So then those storm events, they can be very damaging, but in terms of the ecology, it resets the system.
Right.
Yeah. When the Hurricane Ivan passed by just east of the Mobile Bay, at that time I had some mooring instruments in the water, and by the time that I decided to take them out of the water, it was already too late. So that according to the safety protocol, I could not ask the divers to get into the water.
Right.
Yeah. So I just crossed my fingers, and then about 7 to 10 days after the landing of this hurricane, we went in, and then we did a really good job. All the instruments were in the water. Yeah. So we put a really huge truck tire filled with the cement as an anchor. So that turned out to be exert a strong
Right.
enough force to hold everything. So
and then you got the data during
yes,
the hurricane event.
So that we published 2 papers out of those papers. Basically, what we saw from those numbers was that the Mobile Bay was reset almost completely.
That's so interesting.
Yeah, so that all those bad things that we put into the Mobile Bay
Mm-hmm.
in the previous years, almost all of them were flushed out of the system. Yeah.
That's really interesting.
Especially the Gulf of Mexico estuaries, they tend to be very shallow.
Mm-hmm.
The Mobile Bay 3.5 meters, here 3 meters, so that it's not that difficult for the storm surge or the wind to flush everything out of the system.
Mm-hmm.
Yeah, over that about 2 or 3 day time period.
Wow.
Yeah. So having such a the occasional the flushing mechanism in place, then we don't really need to pay that much attention to the water quality, at least not as much as they do on the East Coast.
Right.
Yeah.
That's interesting.
So and then again that the fishery is such a large industry here.
Right.
So that people will better pay attention to the living resources there.
Right.
Yeah. So since you mentioned about some papers,
Mm-hmm.
How many papers do you think in your mind?
Probably one.
Just the one.
Yeah.
Okay. Then let me give you about 3,
Okay.
and then if you like to give just one to them, why don't you select one?
Okay.
Because what I'm thinking is these students are probably U2 students. This is for course 281, right?
That's right.
Yeah.
Mm-hmm.
Then so that I don't like to really bore them with some purely physical paper with a lot of mathematical equations in there.
Right.
But since that's where I come from, I like to suggest one to you
Sure.
in that field.
To demonstrate it. Mm-hmm.
And then another one would be the modeling of some non-physical processes.
Okay.
Yeah. And then third one is a more topical thing, like the effect of hurricanes or something.
Excellent.
Yeah.
That sounds very
So
interesting.
let me give you 3, and then please use them in any way you like.
Okay.
Yeah.
That sounds great.
Mm.
Well, anything else you'd like to add about your research or students knowing
So
you?
what I'm doing right now,
Mhm.
I have been very slow, not being able to spend much of my time on my research. But what I'm slowly but continuously doing is I've been working with the Sam Brody and Bill Merrill
Mm-hmm.
about the Ike.
That's great.
So I'm developing a hydrodynamic model for the Galveston Bay. This is about to be done. So I think probably by the end of this year, I'll be able to say that I have a good 3-dimensional hydrodynamic model for the Galveston Bay. What it does is that it's going to calculate how the water moves up and down, what is the water current velocity, and the salinity and temperature.
Mm-hmm.
Those are considered to be physical parameters.
Right.
So this model will be able to calculate that for the entire Galveston Bay.
Do you think that the Ike Dike will change the movement of the water much?
That's the whole idea here.
Mm-hmm.
We first need to develop such a model for the current condition of Galveston Bay.
Right.
And then once I feel confident that I can convince other people about the credibility of this model, then within this model I can build in the Ike Dike.
And will that change, like
Then-
for
then-
example, the functioning of storms, flushing out the system and things like
All
that?
those are things. So then I will have 2 versions of the model. One version would be the Galveston Bay as it is now.
Right.
Another version would be this one plus the Ike Dike. And then I can do so-called the whole bunch of the scenario runs
Right.
comparing these 2.
That's excellent.
Yeah, so that's what I'm doing right now. Yeah, I have a postdoc joining me as of September 1st.
Mm-hmm.
So
Great.
I can get back to work.
I love it. Thank you so much for your time.
Thank you.